All right, today we're going to jump into a story that kicks off with something you could literally doodle on graph paper, just drawing shapes on a grid of points. But what we're going to find is that this simple idea uncovers a connection that is, well, surprisingly deep and really elegant. So here's the central puzzle for today. There's this very specific family of polygons, shapes you can draw on a grid, and every single one of them, no matter how different they look, is tied together by a secret rule. A rule that always involves one particular number. The question is, what is that number? Yup, it's 12. It just seems to pop up out of nowhere, but it is absolutely the key to this whole thing. And today, we're going to figure out exactly why this number shows up every single time with perfect consistency. Okay, so to solve this mystery, we first need to kind of map out the territory. We're going to start with a classic, super elegant theorem that looks like it gives us a perfect formula for these grid shapes, right before we see it all fall apart. So the main characters in our story are called lattice polygons, and they are pretty much exactly what they sound like. They're polygons where all the corners, all the vertices, sit neatly on points with integer coordinates. 1, 2, 3, 5, that kind of thing. Nice and simple. Now check this out. This is Pick's theorem, and it is just a beautiful little formula. It gives you this incredibly simple way to find the area of any of these lattice polygons just by counting points. You count the integer points inside the shape, that's I, and the points right on its boundary, that's B. It's this amazing bridge between something continuous, like area, and something discrete, like counting dots. But here's the twist. This gorgeous rule that works flawlessly in 2 dimensions completely and utterly fails as soon as you go to 3. You can actually build these shapes called Reeve's tetrahedra that have the exact same number of lattice points on their vertices and inside, but they have totally different volumes. It's a total deal breaker. And this failure proves there's no simple 3D version of Pick's theorem. It tells us that to find the deeper patterns, we have to look somewhere else. And that brings us right to the heart of our mystery. We're going to zoom in now on a very, very special class of lattice polygons, the ones where this strange constant, this number 12, finally steps into the spotlight. These special shapes are called reflexive polygons. They've got 2 main rules they have to follow. 1, they have to be convex, so no weird, dense, or inward curves. And 2, they contain exactly 1 integer point on their interior. And for simplicity, we just put that point right at the origin. Out of all the lattice polygons you could ever draw, these are the ones that are holding the secret. Now, here's where it gets really cool. For every one of these reflexive polygons, which we'll call P, we can build a partner shape, called its dual. The way you do it is, you take the vectors for each boundary point. Then you find the difference vectors between one point and the next. And the shape you get by connecting those new vectors, that's the dual polygon. And it turns out the dual of a reflexive polygon is always reflexive too. And this brings us to the big moment, the big reveal, the 12-point theorem. It says that for any reflexive polygon you can possibly dream up, if you count the number of lattice points on its boundary, and then you add that to the number of lattice points on its dual's boundary, the sum is always, without fail, 12. And this isn't just a coincidence. It holds for every single one of the 16 possible types of reflexive polygons. Take a tiny triangle. It has 3 boundary points. Its dual has 9. Add them up, you get 12. Or a special hexagon that happens to be its own dual. It has 6, its dual has 6, still 12. A square has 8, its dual has 4. The sum is always 12. It's a perfect, unwavering rule. So we've seen what the rule is. But the real question, the one I know you're asking, is why? Why on earth is it 12? Is this just some cute little numerology trick that happens when you count points on a grid? Let me put that another way. We found this perfect invariant. Is it just a fluke of combinatorics? A neat pattern? Or is it a clue that's pointing to something much, much deeper? The answer is a hard no. It's not a fluke at all. This number 12, it isn't a coincidence. What it is a 2-dimensional shadow of a fundamental principle from a whole other field. Algebraic geometry, and specifically the theory of toric varieties. To really get why, you need what's called a toric dictionary. It's this amazing translation between our simple polygons and the language of complex surfaces. In this dictionary, the number of boundary points, that L of P, it's not just a count anymore. It actually represents a super important topological invariant called k squared, the self-intersection of the canonical divisor. And the boundary points of the dual? That corresponds to another fundamental property, C2, the second Chern class. So when we write down our simple little formula about boundary points adding up to 12, what we are actually writing in the language of algebraic geometry is k squared plus c2 equals 12. And that is a famous fundamental equation called Noether's formula for these kinds of surfaces. The number 12 isn't random. It's a structural constant baked into the topology of surfaces. Our little polygon theorem is just a beautiful, tangible reflection of that deep fact. So, we've solved our mystery. We know where the 12 comes from. But like any good discovery in science or math, this solution doesn't end the story. It actually just throws the doors wide open to this huge landscape of active, cutting-edge research. See, our reflexive polygons are just the flat, 2D versions of things called Fano polytopes. And these polytopes are considered the fundamental atomic building blocks of higher dimensional geometric objects. And that duality we saw between a polygon and its partner, that's a simple preview of the duality at the very heart of mirror symmetry, which is a mind-bending concept that connects geometry to string theory. And just to give you a sense of the scale we're talking about, in 2D, we found there were only 16 of these reflexive polygons. Well, in 3D, after a massive computer search, they found 4,319 of them. And in 4D, the number explodes to over 473 million. Just classifying and trying to understand these things is a massive ongoing challenge. So let's end on this thought. We started with dots on a grid, and we stumbled onto a shadow of a fundamental law of topology. It really makes you wonder, right? What other profound truths, what other physical or mathematical laws are just sitting there waiting to be found, hiding in plain sight in the patterns of the simplest shapes we can possibly imagine?